After the completion of free electron theory of metals, today in solid state physics, we are going to start a new chapter, band theory of solids. Actually, this band theory of solids is a very important concept in solid state physics. You know, the free electron theory, which we have discussed in very detail in our previous lectures, the application of this theory is limited only to metals, not for insulators, not for semiconductors, but only to metals. But you will see that this band theory finds its applications in explaining the behavior, the properties of all types of materials, that is conductors, that is metals, semiconductors and insulators. Okay, and this is our first lecture on this band theory of solids. So in this first lecture I will only introduce you this band theory of solids. So this is just a brief introduction regarding this band theory. So a obvious question arises, why we need band theory if already we have free electron theory to discuss the properties of solids, then why we need band theory of solids? The answer is obvious. Whenever a new theory comes into origin, definitely there will be some drawbacks, some shortcomings in the previous prevailing theory. So it is obvious that there will be certainly some shortcomings or drawbacks of free electron theory, due to which we need a new theory, and the new theory which replaced the free electron theory is called band theory. So first of all, we will know about the shortcomings or drawbacks of free electron theory. Although you have seen that the free electron theory, which we have discussed in our previous lecture in very detail, was successful in explaining the various electronic and thermal properties of metals. You have seen we can discuss successfully the electronic specific heat, spin paramagnetism, Hall effect, electrical conductivity, thermal conductivities, and many more properties of metals on the basis of this free electron theory. And all these properties of metals were successfully explained. But as I have told you that this theory is unable to explain some of the properties of materials like insulators and semiconductors. It means if you will try to explain the properties of insulators, when you say insulator, that means a material which does not conduct electricity. Okay, and semiconductors are materials which do not conduct electricity at 0 Kelvin temperature, but with rise in temperature it starts conducting the electricity. So the properties of insulators and semiconductors cannot be explained successfully on the basis of free electron theory of metals. Why this free electron theory fails in explaining the properties of insulator and semiconductors? You can think it like this. Because by definition, you know that when you say free electron, this term free electron means an electron free to roam around and conduct electricity. Okay? But the main job of an insulator is not to conduct electricity. Okay? A model explaining the absence of electrical conductivity will have to comprise electrons and electrons unable to move freely. Okay, so a theory in which is able to explain that materials will be not electrically conducting, which will have electrons unable to move freely. Only that theory can explain the behavior of particularly the electrical behavior of an insulator. Okay. And what about the semiconductors? When you talk about semiconductors, you know they are neither good conductors nor insulators, because I have told you that at 0 Kelvin temperature a semiconductor behaves like an insulator, but even at room temperature or higher temperature it conducts some electricity and behaves like a conductor. So the behavior of a semiconductor is more mysterious. It is full of mysteries, and that can't be explained by the help of free electron theory of metals. Okay. So apart from that, it is also seen that the resistivity of insulators varies with temperature. But how this resistivity of insulator varies with temperature, that cannot be explained on the basis of free electron model. Okay. So these were the reason why we need a new theory. In spite of free electron theory, already we have free electron theory, but you can see the free electron theory can be applied to explain various electrical and electronic and thermal properties of metals only, not of insulators and not of semiconductors. And that's why people needed a theory which can explain the behavior of semiconductors and insulators. And that theory which actually successfully explains the electronic and thermal properties of semiconductors and insulators, that is called band theory. But we will also like to know what was the reason of failure of free electron theory. Why this free electron theory was failed in explaining the properties of all types of materials. What was the key reason behind this? Actually, the failure of free electron model is due to the oversimplified assumption that conduction electron in a metal experiences a constant or zero potential due to the ion cores and hence is free to move about in a crystal. This is the key point. You have learnt already these things in free electron theory of metals, and you have seen whenever we apply the free electron theory of metals, you imagine that our electron of valence electron of metal is confined inside a potential box, and the potential experienced by that electron inside the potential box is zero. We have considered that V is equal to 0 or constant. Okay. And due to that, since the electron is moving in a region where its potential is 0, it means it does not interact with the ion cores and with one another. And that's why the electron moves freely. This behavior of potential inside the solid is not correct. In fact, potential inside the solid is not constant or it is not 0. Okay. But in free electron theory, this simple version of potential was assumed, and that's why this theory fails in explaining the behavior of insulators and the semiconductors. Okay. So the key point why this theory was failure is what? The assumption that V is equal to 0, that is potential experienced by the electron is 0 inside a solid. this assumption is incorrect. So definitely we should know what is the reality, what is the actual behavior of potential. So in fact, it is seen that potential due to ion cores is not constant. This is the reality. It is not constant, but it may change with the position of the electron in the crystal. It means as the electron moves inside the crystal and it goes to different positions, the potential varies accordingly. Actually, the contribution to this potential is also due to the other free electrons. When you are talking about a particular electron, let us say this is your electron under consideration, then the remaining free electron also contribute to the potential. So there are two sources of potential. One is due to the ion core, and the potential created by the ion core, it does not remain constant, but it varies in accordance with the position of the electron. Okay. And the other source of potential is the other electrons. It means if you are talking about the motion of this particular electron which I have made here, then the remaining electrons which I am showing here also contribute to its potential. Okay. So you can see that the actual nature of potential under which the electron moves in a crystal is very complex, very complicated. It is not so simple that you can take V equal to 0. That was oversimplification. So this assumption V equal to 0 of free electron theory of metals was not correct, and that's why this theory is not a universally accepted theory to deal with the behavior of all types of materials. Okay. So actually, what is the actual behavior of potential? You can see that, as I have told you, that this potential is contributed by two sources, ion cores and electrons and the free electrons. And so in general we say that the nature of potential is very complex, very complicated. Okay. In fact, you can say that the potential experienced by an electron in a crystal is assumed to be periodic, and the period of this potential is equal to the lattice constant, as you can see in this figure. Actually, in this figure I have shown the one-dimensional representation of potential experienced by an electron in a perfectly periodic crystal lattice with lattice constant A. That has been shown in this figure. You can see that the potential near the surface, here I have mentioned surface, so near the surface there is a violation of periodicity of this potential. Okay. What will be the shape of this potential near the surface? I have shown here that it deviates from its periodic nature. Why at the surface the nature of this potential variation changes is that because there is an interruption in the periodicity of the lattice at the surface. So due to this interruption in periodicity of the lattice at the surface, the shape of the potential does not maintain its strict periodicity and have some irregularity, but this irregularity in potential is not very important. This irregularity of potential at the surface is generally not accepted, generally not taken into account, but we in general ignore it. Okay. So as a whole you can say that the potential inside a solid varies periodically, and the period of that potential is same as that of the lattice constant A. Okay. Actually, this assumption is based on the fact that the ion cores in a crystal are distributed periodically on the lattice side. As you can see in this figure, that all these small spheres actually represents the lattice site, and these are regularly arranged. The distance between any two successive lattice point is A, which is called lattice constant. Since the lattice points are periodically distributed, and due to this, at the lattice point ion cores are attached, and ion cores are responsible for this potential. That's why this potential has a periodicity equal to the lattice constant. This is the reason. Okay. In fact, in this theory, it is assumed that the potential contribution due to all other free electrons is constant. Okay. Potential due to the ion cores varies periodically with a period equal to the lattice constant, but potential contribution due to the other free electrons is assumed to be constant. Okay. In fact, this type of periodic potential extends up to infinity, okay, in all directions except at the surface. As you have seen that at the surface of the crystal there is some irregularity in the potential variation, and that is due to the interruption in periodicity of the lattice, and it has a shape similar to as you can see in this figure which I have mentioned here. Okay. And but I have also told you that this type of potential irregularity is ignored. Okay. So now we will know what is the basis of band theory. Okay. On which basis this band theory has been proposed or developed. Now we will see it. In fact, the periodic potential under which the electron moves is the basis of band theory. So in band theory, we always assume that potential inside the crystal is not constant, but it varies periodically. This periodic variation of potential is the basis of band theory. This is the key point of band theory, and considering this periodic variation of potential, we will be able to explain each and every aspect of different type of materials. Okay. In fact, the behavior of an electron in this potential is described by constructing the electron wave functions using one electron approximation. One electron approximation, it means what? Actually, in band theory of solids, there are several elementary derivations, each giving a slightly different picture. Okay. But this band theory essentially involves the single electrons. It means we will always talk about the motion of a single electron. So it is said that band theory is based on one electron approximation. Okay, one electron approximation. And in this approximation, the total wave function for the system is obtained from a combination of wave functions, each one of which involves the coordinates of one electron. Okay. In other words, you can say that the field experienced by a particular electron is assumed to be the resultant of field due to fixed nuclei and the average field due to the charge distribution of all other electrons. Okay. As we will discuss in our forthcoming videos, the motion of an electron in a periodic potential yields the following results. These results will be discussed in very detail in our forthcoming lectures, but here in this introduction I have mentioned what we will get when we will apply the proper theory of this band theory. Okay? In fact, there are two main results of this band theory. The first one says there exists allowed energy bands separated by forbidden regions or band gaps. As you can see, in contrary to the free electron theory of metals, we have seen in case of free electron theory, we were talking about discrete energy levels. These lines represent the discrete energy levels in free electron theory of metals. But in band theory, we do not talk about the energy levels, but we talk about energy bands. Electrons are distributed in energy bands, not in energy level, according to band theory. But these allowed energy band means the energy band in which electron exist. These are not continuous, but any two allowed energy band is separated by a forbidden region. That in that forbidden region there can be no electron, and that is called either the forbidden energy gap or band gap. So you can see here I have shown two allowed energy band, and that is separated by a band gap or a forbidden energy gap. So this is the main feature of the band theory, that in solids there are allowed energy bands and two successive allowed energy bands are separated by a band gap or a forbidden region. When you say forbidden region, it means the region where there is no electron. Okay. And the another important result which we will see in our later videos is the electronic energy functions E of k, where k vector k is the wave vector, are periodic in the wave vector k. It means energy of electron varies periodically with wave vector k. In fact, you can see that these results are not in agreement with the results of free electron theory, but it differs. It is just contradictory to the result of free electron theory, in which you have assumed V equal to 0. Actually, you have learned in your previous lecture on free electron theory of metals that the energy of a free electron varies with the wave vector k according to this relation, E equal to h bar square k square over 2m. This is nothing, you know, this E is equal to p square over 2m. This is simply kinetic energy. P is momentum of the electron. And you know, according to quantum mechanics, momentum of this electron P is equal to h bar k. So this is h bar k over m. Okay. And since there is p square, so this will be h bar square k square over 2m. This is the result which we see in free electron theory of metals. And you can see, according to this result, there will be no upper limit of energy. Why there will be no upper limit? Because this k has discrete values. And if k has discrete values, the energy levels of the electron will be also discrete. And you will also see that the spacing between two energy levels is not constant. It may have any value. Okay, and the upper limit of energy is not defined. It may be even infinity. For example, you have seen uh, the problem of electron inside a one-dimensional potential box in free electron theory of metals. Actually, we have started our problem of free electron theory of metals from this concept. And you have seen, if we assume that a free electron is confined inside a one-dimensional potential box of length L, like this, here V is infinity, here V is 0, and we consider that there is an electron inside this, and L is the length of this box. Then you have seen that in the energy of electron in nth energy level is given like this. This is n square pi square h bar square over 2 ml square. Okay. Here n is the quantum number having values 1, 2, 3 and so on. Okay. So substituting the values of n, you can find the energy of electron in different energy levels. So in first level, you will take n equal to 1 and energy is this much. That is pi square h bar square over 2 ml square. And when n is equal to 2, then energy of electron is E2, and that will be equal to 4 pi square h bar square over 2 ml square, which is, you can see, is equal to 4 E1. Okay. And similarly, if we take n equal to 3, E3 is equal to 9 E1. And if you will take n equal to infinity, this energy will be simply infinity. So that it has been told here that there is no upper limit of energy in free electron theory of metals, and the energy levels are discrete. Now let us see. This is your first energy level, that is for n equal to 1. This is your second energy level. This is third energy level. This is fourth energy level. And the energy of electron in these levels are E1, 4 E1, 9 E1, 16 E1, you can see. Now, the separation between the first and second energy level, this will be what? This will be E2 minus E1, which is 3 E1. Okay? And the energy separation or energy gap between the second energy level and the third energy level will be E3 minus E2, and you can see this will be 9 E1 minus 4 E1, that will be 5 E1. And the separation between third and fourth energy levels, that will be what? That will be 7 E1. So you can see that the separation between two successive energy levels is not constant. Okay. So these were the results of free electron theory of metals. But band theory does not agree with it. Actually, according to band theory, this energy E of electron varies periodically, not in this discrete manner. It varies periodically with wave vector k. And so, if its variation is periodic, the upper limit will be fixed. It will be never infinity. So the results of the free electron theory of metals contradicts with the result of band theory of solids. Okay. In fact, this band theory of solids is based upon 4 models. Okay. 4 models are used to discuss this band theory. And what are those 4 models? Those 4 models are Bloch's theorem, Kronig-Penney model, which is popularly known as KP model. Third one is called Zeeman model, and the fourth one is Feynman model. But in syllabus of any University of India, particularly for the students of B.Sc and M.Sc level, these 2 models are not to study. Actually, these are advanced theory which is excluded from the syllabus of the students of graduate and postgraduate level in India. Okay. Only these 2 models are in your syllabus. So in fact, I will not provide any video on Zeeman model and Feynman model. We will see only the concept developed on the basis of Bloch's theorem and this KP model. Okay. So, what is this band theory? Why it was needed? What were the drawbacks of free electron theory of metals, and how it was overcome in band theory? All these things you have learned in this short video on the introduction of band theory. Okay, and I hope definitely now you have an idea about this band theory, how much it is going to be useful for you, and for the discussion of the properties of the materials like semiconductor, like insulator and metals. Actually, this band theory or in this band theory you can see there is an existence of band gaps, and the existence of this band gap is the most important new property which emerges from the free electron model in extended to include the effect of periodic potential of the ion cores. It will be shown later on in my videos that these band gaps result from the interaction of conduction electron waves in ion cores of the crystal and are of decisive significance to determine whether a solid is conductor, a semiconductor or an insulator. Okay. So we can easily differentiate between these three materials on the basis of this band gap or energy gap. Energy gap or band gap is responsible for the particular nature of the material. So this is actually of very great importance. And besides this, we shall also encounter in our forthcoming concepts the other remarkable properties of electrons in crystals. Okay. So in our forthcoming lecture, first of all, we will learn about this Bloch's theorem, and after that we will learn about this Kronig-Penney model and their applications. Okay. So I think we have now an idea about this band theory in clear cut in your mind, and you will definitely enjoy the forthcoming videos regarding this band theory of solids. Okay. Thank you very much.